Einstein's theory of relativity is based on two principles. The first principle is that if you have two objects and nothing else, then it's not possible to tell which object is moving and which object is standing still. This is true even if one of the objects is an entire planet. From the perspective of Adam in the spaceship is standing still, and it's the planet that's moving. There is no experiment Adam can perform to let him know if he is moving. For example, if he throws a ball up in the air, it'll go straight up and down just as if he was standing still. From the perspective of Sarah, the ball is already moving with the spaceship, and the ball keeps its forward momentum when Adam throws it up in the air. This is why, from Sarah's perspective, the ball looks to Adam as if it is moving straight up and down. Adam's view that the spaceship is standing still is just as valid as Sarah's view that it's the planet which is standing still. After all, from the perspective of a third observer, it's the sun which is standing still, and both the planet and the spaceship are moving around it. And from the perspective of a fourth observer, the sun is moving at great speed through the galaxy, along with the planet and the spaceship. In general, any observer can believe that they're standing still, and that the rest of the universe is moving around them. And every observer is equally correct. It's not possible to tell which object is moving, because in the absence of a force, all objects will continue moving in the same direction with the same speed forever. Objects slow down here on Earth only because of the force from friction and air resistance. Einstein's theory of relativity is based on two principles. The first principle is that it is not possible to tell which object is moving and which object is standing still. Every observer is correct in thinking that they are standing still and the rest of the universe is moving around them. The second principle that Einstein's theory of relativity is based on is the speed of light is the same for all observers. Suppose Adam fires a laser at the ground, which bounces off a mirror, and he measures the time it takes for the light to return to the spaceship. From Adam's perspective, the laser light goes straight up and down. From Sarah's perspective, the laser light follows a V-shaped path. The V-shaped path is longer than the straight up and down path. Since the speed of light is the same for all observers, from Sarah's perspective it takes a longer amount of time for the laser light to return to the spaceship. But if Sarah looks at Adam's clock, she will see that his clock reads less time in between when he fired the laser and when he received the reflected light back. This means that Sarah will see Adam's clock running slower than her own clock. The closer that a spaceship approaches the speed of light, the slower the time inside the ship will flow. If the speed of the spaceship was equal to the speed of light, then time inside the ship would stop altogether. No matter how fast the spaceship travels, Adam will never notice that time for him is going slower. Everything is slower by the exact same amount, including the speed of his thoughts. So time for Adam appears to be flowing normally. From Adam's point of view, his ship is standing still, and it's the rest of the universe that's moving. Therefore, Adam will think that everyone else's clocks are moving slowly. Suppose there are 3 ships moving together, and Adam fires a laser to the 2 other ships. From Adam's perspective, all 3 ships are standing still, and the 2 other ships will receive the laser light at the same time. Sarah sees the light from both lasers move at the same speed. Therefore, Sarah will see the left ship receive the laser light before the right ship. But we know that the clocks on the 2 ships read the same time when they each receive the laser light. This means that Sarah must see the clock on the left spaceship running ahead of the clock on the right spaceship. From Sarah's point of view, time on the left ship is running ahead of time on the right ship. From Adam's point of view, the time on both ships is the same. Suppose that Adam sends a command for all the ships to fire their engines at the same time. From Adam's point of view, all the ships accelerate together, and the distance between them stays the same. From Sarah's point of view, time on the left ship is running ahead of time on the right ship. Sarah will see the left ship accelerate first, and the right ship accelerate last, and the distance between the ships will shrink. Each spaceship can be thought of as being made up of smaller spaceships, with the distance between them shrinking as they move faster. The closer a spaceship approaches the speed of light, the shorter it becomes. No matter how fast the spaceship travels, Adam will never notice that his spaceship has gotten shorter. Everything inside the spaceship has gotten shorter by the exact same amount, including Adam himself and all his rulers, so everything inside the spaceship will look normal to Adam. From Adam's point of view, his ship is standing still, and it's the rest of the universe that's moving. Therefore, Adam will think that it's the rest of the universe that's gotten shorter. If Adam is moving at almost the speed of light, then from Sarah's point of view, time inside Adam's ship will almost stop completely. From Sarah's point of view, Adam will travel the length of the entire universe while his clock moves forward by only a few seconds. From Adam's point of view, time inside his ship is running normally. To Adam, the length of the universe passes in a few seconds because the length of the entire universe has shrunk to almost zero. Suppose two ships throw identical balls at each other. The balls bounce off each other and return to each ship. From Sarah's point of view, time on Adam's ship is moving slowly. From Sarah's point of view, Adam throws his ball much more slowly. From her point of view, Adam's ball and everything on Adam's ship must have more mass. Otherwise, Adam's ball wouldn't have had enough momentum to cause her ball to bounce back. This is the meaning of E equals mc squared. As an object moves with more energy, its mass increases. This is why nothing can travel faster than the speed of light. As an object gets close to the speed of light, its mass becomes so big that an infinite amount of energy would be required to move it faster. So far, we've only been talking about cases where Adam's ship moves without changing speed. But if the ship tries to change speed, then things are different. When Adam fires his rockets, the acceleration causes him to be thrown back in his seat. From his point of view, the spaceship is standing still, and it's the rest of the universe which is accelerating. From his point of view, there must be a gravitational field causing the entire universe to accelerate. From Adam's point of view, it is this gravitational field which is causing him to be thrown back in his seat. From Adam's point of view, the force from his rockets exactly balances the gravitational force, causing his ship to stay in the same place. Adam sees the entire universe affected by this gravitational field, including rays of light. Since light must be the same speed for all observers even though it is affected by gravity, this means that gravity must also affect the rate at which time flows. If Adam travels near the speed of light, then time on his ship will flow very slowly. When Adam returns, only a few minutes will have passed for him, but many years will have passed for Sarah. From Adam's point of view, he's standing still, and it's time on Earth which is moving slowly. When Adam fires his rockets to turn around, he will think there is a gravitational force causing him to remain still and causing the Earth to accelerate towards him. From Adam's point of view, this gravitational field is causing time on Earth to run faster than time on his ship. This is why, from Adam's point of view, more time has passed for Sarah than for him. Gravity is not a force, but a curvature in space-time. Objects with mass cause a curvature in space and time. There only appears to be a force, when in reality everything is just following straight lines. In the case of a black hole, the curvature becomes infinite. Not even light can escape. Near the black hole, time stops altogether. The opposite of a black hole is a white hole. We've observed many black holes, but we know of only one white hole. The only white hole we know of is the Big Bang, which created our known universe.